Hello, everyone. Welcome to this lecture of CSEN 1001, Computer and Network Security. This is Dr. Amr Al-Mogi. In our last lecture, we had discussed block ciphers. We have discussed actually different types of encryption algorithms, and we have discussed in details block ciphers, particularly the cipher that is currently the main standard that is used in most systems around the world, which is AES. Today, we are going to continue our discussion of symmetric ciphers. First, we will continue the discussion of block ciphers, and then we will go into the details of the second type of symmetric ciphers, which is stream ciphers. So, in this lecture, hopefully by the end, you will understand a concept that is very important in symmetric encryption and block ciphers in particular, which is the modes of encryption. We will discuss several modes of encryption, and we will discuss their vulnerabilities. We will also discuss the stream ciphers, and the main component in stream ciphers is how to generate pseudo-random numbers. And then we will see a specific type of stream ciphers, which is the RC4 cipher. Okay, we will start today's discussion with the topic of modes of encryption. Basically, last time we discussed AES. And so if we take AES as a black box, okay, we know that AES accepts as input 128 bits of plain text and produces 128 bits of ciphertext. Okay, what changes is just the size of the key. Okay, so the size of the key can be 128, 192, or 256. Okay, however, the size of the input and the size of the output, the plain text and ciphertext, are the same. So if we just want to encrypt 128 bits of data, we know exactly what we should do. However, 128 bits, as you probably know, is a very small amount of data. Typically, we want to encrypt much more. You want to encrypt megabytes or gigabytes of data so that you can send them or you can communicate them with someone else. And so now this begs the question. If you have more than 128 bits of data to encrypt, how should you actually encrypt them? How should you pass them to the AES algorithm such that the output of the encryption is still secure? Because it turns out that the way that you pass several blocks of plain text to the encryption algorithm has a significant impact on the security of the encryption algorithm or the output of the encryption algorithm. It may be the case that AES is a very secure encryption algorithm, and it is. It doesn't have any known weaknesses in terms of cryptanalysis. And the size of the key is large enough such that brute force is unlikely. And so AES itself is a secure algorithm. However, as we know in security, the algorithm itself is not the only component. It's also about how you use the algorithm. If you use a secure algorithm in a wrong way, then you will end up with having vulnerabilities. And so, modes of encryption is the topic that is supposed to determine how you are going to use an encryption algorithm to encrypt several blocks of data. We will discuss several modes of encryption just so that we see the difference. And the first mode is the simplest mode, which is called the electronic codebook mode of encryption. Basically, you have your encryption algorithm, for example, AES. And let's say you want to encrypt several blocks of plain text, and in this case, every block will be 128 bits. How can you pass these sequences of blocks to the encryption algorithm? The electronic codebook mode is a very simple one. It basically says, take your data, divide them into blocks of 128 bits, and very simply pass the blocks independently to the encryption algorithm, just as you see in the figure on the right, the top one. You take the block of plain text P1, which is 128 bits, and you pass it to the encryption algorithm together with the key, whatever the size of the key is, it doesn't make a difference. And out comes C1, which is also 128 bits. If you want to decrypt, you pass C1 to the decryption algorithm of AES, out comes P1 again. If you want to encrypt more, you take the second block of data, which is also 128 bits, P2, of plain text. You pass it to the encryption algorithm, which is, of course, AES, with the same key. And it's actually the same key that was used with the first block. The key doesn't change. And out comes C2. If you want to decrypt, you pass C2 to the decryption algorithm, out comes P2. Okay? And you keep doing that for as many blocks that you want. So this is simple, straightforward. Doesn't seem that there are actually any problems. However, once you actually examine the details of this mode of encryption, you will find actually significant vulnerabilities. Consider the case that you have a block of data, let's say, for example, 1000 bits. Let's say you have 1000 bits of data, and there are actually a lot of repetitions, meaning that, for example, the first 500 bits are all zeros. Okay, half the data are zeros. So if you are going to encrypt 500 bits of zeros or 500 bits of whatever they are, what would you do? You would basically pass each 128 bits to the encryption algorithm, and out comes the ciphertext. Now, think about this for a second. What would happen if you pass identical blocks of plain text to the same encryption algorithm with the same key? What would happen if you pass the same 128 bits of data, meaning that P1 and P2 are actually identical, to the same encryption algorithm with the exact same key? The result would be that C1 and C2 would actually be identical. So even though you are encrypting actually different blocks, because the plain text is identical and the key is the same, the result of the encryption will be the same. So what would be the problem there? Consider the figure that you see at the bottom. Let's say you are trying to encrypt this image. Okay, it's the image of a penguin and the background is all white. So once you encrypt it, these white pixels are going to be entered as blocks of plain text, whatever the value of the color white is. Okay? There will be 128 bits representing the color white. And then the next 128 bits will be representing another group of pixels, which is also white, and will be passed to the same encryption algorithm. The result of the encryption is as you see it here. It's actually the case that because you are encrypting the same or identical blocks of data using the same key, the result will be something that is not really hidden. Even though this is an encrypted image, you can actually see exactly what the image is. Okay? Or you can infer its content, even though the encryption has been successful. So this is an example of a secure encryption algorithm such as AES, but used in a wrong way. So if you are actually encrypting blocks of data using AES, but this data has a lot of repetitions and has patterns, then using the electronic codebook mode will result in a vulnerability. The desirable form of the encrypted image would be what you see on the right, something that is completely pixelated. You cannot really see anything. Okay, but ECB will not achieve that. And so this is then the first mode of encryption. It is okay to use when you are encrypting small amounts of data, 1 or 2 blocks basically. If there are no patterns between them, then you're okay. There will not be a problem. But if you're encrypting large blocks of data and there are likely going to be patterns of identical plain text, then you will get identical ciphertext as well, and you will see the vulnerabilities there. The second mode of encryption deals with this challenge, and it's called the cipher block chaining mode. Basically, if you want to encrypt a block of plain text, let's say you're trying to encrypt P2, before passing it to the encryption algorithm, which is AES, you XOR with the last block of ciphertext. Okay, so if you want to encrypt a plain text block, you XOR with the ciphertext block before it. So what you pass to the encryption algorithm is not P2, but actually it is P2 XORed with C1. This is what you pass to the encryption algorithm. Okay, so you pass P2 XORed with C1 to the encryption algorithm, out comes C2. If you want to encrypt P3, before you pass it to the encryption algorithm, you XOR it with C2. If you want to encrypt P4, you XOR it with C3. Every block is XORed with the ciphertext block that is the output of the stage before it. Okay, so block Pn is XORed with Cn-1 before being passed to the encryption algorithm. Okay, so if you're going to do that, you will actually run out of blocks in the very first block. So how do you encrypt P1? You have to XOR it with something. There is no block before it. There is no ciphertext block before it. So for the first block only, you XOR it with something called the initial value. The initial value, or the initial vector, is a value that is chosen. It has the same size of the plain text. So if it's AES, it's going to be 128 bits. And it is used for the XOR in the first block only. And the initial value has to be chosen in a secure way. So it does not necessarily have to be a secret value, although in some applications it has to be. But sometimes, for example, it has to be unpredictable, so that an attacker would not be able to guess it and cause problems in the encryption. Usually what we say is you shouldn't use this combination of the same initial value and the same key several times. Because what would happen is, if you have the same initial value and the same key, and if you have identical blocks of plain text, so P1 and P2 and P3 are the same, you would actually end up with the same problem of the electronic codebook mode. You will have patterns, even though the patterns may actually occur over a longer duration, but you will still actually have patterns. So you have to change the initial value every time you encrypt using the Cipher blockchaining mode. Okay? What does this do? How does this actually fix the problem of the electronic codebook mode? Basically, if P1 and P2 are identical, in the electronic codebook mode, C1 and C2 would also be identical because you are passing both blocks to the same encryption algorithm with the same key. But consider what is happening here in the Cipher blockchaining mode. If P1 and P2 are identical, you XOR P1 with IV and out comes C1, and you XOR P2 with C1, out comes a different value that is encrypted, and this leads to C2. So even though P1 and P2 are identical, C1 and C2 in this case will not be identical, because what you pass to the encryption algorithm is not actually P1 and P2, but two different values that are not identical to each other. In the first stage, it's going to be P1 XORed with the initial value. In the second stage, it's going to be P2 XORed with C1. Okay, so if you are encrypting different values, then the output of this encryption will definitely also be different. And so even if you have patterns in the text, the output of the encryption will not actually be the same, and you have actually cured the problem of the electronic codebook mode. Okay, how do you decrypt? So if the receiver receives C1, when you want to decrypt using one of the modes, you basically have to reverse the process. So if you look at the encryption process of C1, the stage before it, or the step before it, was the encryption step. So if you want to decrypt, the first step in the decryption would be to pass C1 to the decryption algorithm, okay, which is also the decryption algorithm of AES. Okay, so you have decrypted. What was the stage before encryption? Here, it was actually the XOR of P1 and IV. So if you want to retrieve the plain text, so P1 XORed with IV is the input to the encryption algorithm. Okay. If you want to retrieve the plain text, if you want to get P1 back, what would you do? You have to XOR the input to the encryption algorithm with the IV. Okay. This is exactly what happened. You pass C1 to the decryption algorithm of AES, out comes a value. This value is XORed with the IV to obtain the plain text back. So you are just actually reversing the stage. If you want to decrypt C2, what do? So if you see the encryption process of C2, the step before C2 is encryption. So the step after C2 in the decryption process would be just the decryption using AES. The step before encryption here was XORing P2 with C1. So the step after the decryption algorithm would be XORing the output here, the output value, with a C1 again, okay, so that you obtain P2. Okay, and you keep doing that. It's still chaining, but you are chaining after the encryption rather than before. After the decryption rather than before the encryption. Okay, so the decryption process is the reverse of the encryption process. Now ask yourself one question. What would happen if there is an error in one of the ciphertext values? So let's say you transmit C2 from sender to receiver, and there is an error that occurs during transmission. For example, an attacker modified a few bits, or there was just errors in the communication channel. So the receiver didn't actually receive C2, but received C2 dash. which is C2 with some of the bits changed from zeros to ones or ones to zeros. What would be the impact on the decryption? How many blocks will be affected? Obviously, if this is C2 dash and you pass it to the decryption algorithm, the output of the decryption algorithm would be very different from the value that would be produced if you pass the C2 without errors. So if the output of the decryption algorithm will be different, then P2 will definitely be different. So if there is an error in C2, then the decryption of P2 will definitely be affected. What else would be affected? If we consider the decryption of C3, you pass it to the decryption algorithm, the output of that is XORed with C2, and out comes P3. If C2 had an error, so instead of XORing with C2, you're actually XORing with C2 dash, which has an error, then P3 will also be affected. So if there is an error in C2, P2 is affected, P3 is also affected. What about actually P4? So if you have C4, now actually I'm assuming here that the error only occurred in C2. So C3 is received without error, C4 is received without error. So C4 is received, it is decrypted, and you XOR it, you XOR the value, the output with with C3. Because C3 was not received with errors, so the output, which is P4, will be okay. So if there is an error in C2, the output of the CBC decryption, which is P2, will be affected, and the next one, which is P3, will also be affected because the decryption of P3 depends also on C2, which has errors. However, P4, which is the output of the decryption of the fourth step, depends only on C3 and C4, so it will not be affected. So an error that occurs in CBC affects the current step and the step after it, but does not propagate any further. So again, the error in CBC affects the current step and affects the step after it, but not any subsequent stages. This is its main problem. Obviously, in the electronic codebook mode, if you have an error in one ciphertext block, it doesn't propagate. It only affects the same ciphertext. So if you have an error in C2, only P2 will be affected. The other blocks will not be affected. So in electronic codebook mode, the error does not propagate to other blocks. In Cipher blockchaining mode, the error propagates to a single additional block. Also, the Cipher blockchaining mode cannot be parallelized. You cannot decrypt P2 without, you cannot decrypt C2 without decrypting C1, and you cannot decrypt C3 without decrypting the one before it, and so on. So the chaining leads to the fact that this cannot be parallelized. Okay. The next mode that we will discuss is called the Cipher feedback mode. It also has chaining, but the goal of the Cipher feedback mode is to convert a block cipher to a stream cipher. Basically, in the electronic codebook mode and the Cipher blockchaining mode, the two modes that we have already discussed, you must have input that is equal to the input of the encryption algorithm. If it is AES, it's going to be 128 bits. What happens if you want to deal with different sizes of input, different sizes of plain text? If you don't want to encrypt actually 128, you want to encrypt something smaller. What would you do? The Cipher feedback mode offers a solution to that. So here, instead of actually encrypting the plain text, you pass the initial value to the encryption algorithm. The output of this, so if this is AES, that's going to be 128 bits. The output is going to be also 128 bits of ciphertext. The output of that is put in a shift register. So if it's 128 bits, you put it in a shift register. Let's say you don't want to encrypt 128 bits. You just want to encrypt something smaller. Let's say S bits. Let's say S is equal to 64. You want to just encrypt 64 bits. So the output of the encryption algorithm is 128 bits, but you want to encrypt only 64. So out of these 128, you just select 64. And you XOR them with the 64 bits of plain text. Out comes 64 bits of ciphertext. Okay. So the entire trick here is that you pass the IV to the encryption algorithm. Out comes 128 bits, but you don't take all of them as ciphertext. You take just whatever you want, and you XOR them with the block of plain text of whatever size you want. It can be 64, it can be 128, it can be whatever you want. Okay, So this is the first stage. What happens in the second stage? You take the discarded bits of the shift register. So if you remember, the first stage of encryption produced 128 bits. That's the encryption of the IV. You used 64 of them. You have 64 remaining. You take those, you put them in the shift register, and you shift it one position to the right. To the left. So you have 64 bits. That is the output of the previous stage. Okay, these 64 bits that were discarded in the first stage, and this remaining 64 bits will actually be C1. Okay, so what do you pass to the encryption algorithm of the second stage? You pass to it a block that half of it, such that half of it is C1, and the second half of it are the discarded bits of the first stage. So you discarded 64 bits in the first stage, and C1 is 64 bits as well. 64 plus 64 is 128. This is what you pass to the second stage of the encryption algorithm. Out comes 128 bits of ciphertext. Again, you want to encrypt only 64 because the size of the input doesn't change. So if you encrypted 64 in stage 1, you will encrypt 64 in stage 2. So you take out of these 128 bits of the second stage, you take from them 64 and you XOR them to produce the second block of ciphertext, which also will have 64 bits. Okay, and you keep doing that. At every stage, you take as input to the encryption algorithm C1 or the ciphertext of the stage before it, concatenated with the remaining part of the shift register that you did not use in the stage before it. Out will come 128 bits. You take from that whatever number of bits that you need to encrypt, or you XOR with the plain text block, and out will come the ciphertext, and you discard the remaining bits. You discard them such that you will actually use them in the encryption of the next block. Okay, this is the encryption part. What about the decryption? If you want to produce P1 back, so you have C1 and you want to produce P1 back. Again, what we do, we take one stage and we try to reverse its process. So how was C1 produced? C1 was produced by XORing P1 with the output of the encryption algorithm. So if you want to produce P1 back and you have C1, you have to XOR C1 with the same output of the encryption algorithm. In other words, you have to reproduce the same output of the encryption algorithm. How was the output of the encryption algorithm produced? You basically encrypted the IV. This is exactly what we're doing in the decryption. You're encrypting IV, out comes the 128 bits that were produced in the encryption. If you're using actually the same key and the same IV, you will have the same output. And you XOR that with C1, and out will come P1. Okay, how do you decrypt P2? So if you look at the stage, okay, how was C2 produced? It was the XOR of P2 with the output of the encryption algorithm. So you want to reproduce the output of the encryption algorithm. If you want to reproduce that, you have to recreate the input. What was the input? It was part that was C1, and part of it were the discarded bits of the shift register of the first round. You actually do the same. You take C1, you put it in the shift register, and the remaining part of the shift register are actually the discarded bits of round 1. And you pass that to the encryption algorithm, you create the same sequence, and you XOR that with C2, out comes P2. Okay? So one important thing to note here about the cipher feedback mode is that you are only using the encryption algorithm in AS in both the encryption part of CFB and the decryption part of CFB. If you go to CBC, in the encryption part of CBC, you're using the encryption algorithm of AS, and the decryption part of CBC, you're using the decryption algorithm of AS, because you are actually trying to reverse the process. Same thing in the electronic codebook mode. You encrypt using the encryption algorithm, you decrypt using the decryption algorithm. However, in cipher feedback mode, you are not actually trying to decrypt using AES, you are actually trying to recreate the sequence that was input to XOR. And so if you use the decryption algorithm of AES, you'll end up with a different sequence. And so the XOR will not produce the same plain text block. So you're using the same encryption algorithm such that the output of that will be identical to what was produced in the encryption part of CFB. So that when you do the XOR, you end up actually with the same block. Okay? Now we ask ourselves the same question that we did in CFB. What happens if there is an error in one block? What happens if there is an error in C1? So C1, let's say instead of receiving C1, we received C1 dash that has some errors. Which blocks will be affected? Obviously, because P1 is produced using the XOR with C1, if C1 has errors, then P1 will definitely have errors. What about P2? In order for you to decrypt and obtain P2, you have to XOR C2 with the result of this encryption algorithm, and the result of this encryption algorithm will depend on C1. And so if C1 has errors, then the input to the encryption algorithm will be different, the output of it will be different, and the XOR will, the result of the XOR will be different, and so P2 will also be affected. What about later blocks? What about P3? To produce P3, you have to actually XOR C3 with the output of the encryption algorithm. So this is the encrypt. Here is the shift register. And here is also the shift register. Okay. So let's assume that C2 and C3 do not have errors. Okay. C3 doesn't have errors. So the content of the shift register that you pass it to the encryption algorithm in this stage will depend on C2, which does not have errors, and will depend on the discarded bits of the stage before it. How were the discarded bits of the stage before it produced? These bits were the result of the encryption step in this stage. Okay, you encrypted C1 dash, which has errors, concatenated with the contents of the shift register from stage 1. Okay. The content of the shift register from stage 1 did not have errors, but C1 had errors. So the result of the encryption now will not be identical to the one that you used in the encryption process. And these same discarded bits, you will use them in stage 3. And so the input to stage 3 will not be identical to the input that was used in encryption. And so P3 will also most likely be different from the one that was used in the encryption. This is actually the main problem of Cipher feedback mode. If you have an error, it is not clear how long the error will propagate for. In Cipher blockchaining, the error only propagates to one position, and we know that. However, in the Cipher feedback mode, because you are using this idea of shift register, and if the contents of the shift register are contaminated, you are actually reusing these contents in the subsequent blocks. So there is no telling when error propagation will actually stop. It could actually infect the entire sequence all the way until the end, or until someone discovers an error and basically tries to fix the content of the block or the content of the shift register. Another problem of CFB is one that it has in common with the CBC block, which is basically that it cannot be parallelized. Every stage depends on the output of the stage before it, and so you have to encrypt serially, and you cannot encrypt in parallel. To fix these two problems, there is another mode of encryption that we have, which is called the output feedback mode. The output feedback mode, basically, you remove the dependency between the stages. So you see here, you encrypt a nonce, and the nonce is basically a random number that is used only once. You encrypt the nonce, and out of that, you XOR a number of bits with P1. You don't use a shift register anymore. You just basically use the number of bits that you want, whatever they are. Out comes C1. Notice here, the chaining doesn't happen with C1. The chaining happens with the output of the encryption algorithm. Okay, so the input, the encryption of P2 is independent of C1. The encryption of P2 doesn't depend on C1. The encryption of P2 depends on the result of the output in the encryption algorithm of the first stage, but it's not dependent on C1. So what you can do is that the part that you see in the dashed box here, you can actually generate it offline. You can just generate a sequence of bits, and you use them to XOR with P1 and P2 as they come. So it can actually be much faster. Because the chaining doesn't happen in the ciphertext, it happens actually at the output of the encryption algorithm. This mode is less secure than CBC and less secure than CFB. The error propagation is actually an advantage here because the errors do not propagate. If there is an error in C1, it will only affect C1 and P1. It will not affect C2 because C2 and P2 do not actually depend on C1. So an error here will not propagate. This is another advantage. And it can be parallelized because the sequence, as we said, can be generated offline. You don't have to wait to generate the sequence when the data comes. You can generate it before any data comes, and you just use them for encryption. Okay. The final mode of operation that we will discuss today is called the counter mode. The counter mode is actually one that is most used in production or in commercial use because it has actually all the advantages. It's fast and can be parallelized, and research has shown that it is just as secure as CBC, which is the most secure mode. So the idea here is very similar to the output feedback mode, but rather than chaining the result of the encryption, you actually just use a counter. And you're using the counter and you increment the counter in every stage. So you're encrypting a counter. You start with an initial value, whatever this initial value is. It's just something that has to be agreed upon between the sender and the receiver. Output of the counter, the counter is encrypted using a key, and the key is also only known to the sender and the receiver. The output of that is XORed with P1, out comes C1. So there is no chaining whatsoever. There is no chaining even at the output of the encryption. There is no chaining of C1 or no chaining of the ciphertext. It can be parallelized. The errors do not propagate. You're only also using the encryption algorithm. So you're not using the decryption algorithm of AES. You're using actually encryption only in encryption and decryption because the goal is to actually regenerate the sequence that you're going to use in the XOR. This is actually the same in OFB. In OFB, you use encryption algorithm of AES in the encryption and decryption of OFB because you are trying to regenerate the sequence that is going to be used in the XOR. Okay. So the counter mode is the one that is most popular. It's used widely. It is very fast. It is quite secure. It achieves actually most of the advantages we are looking for. So the 4 modes of encryption that we discussed achieve the objective of using encryption algorithms in a secure way. So because AES is a secure algorithm, using it by itself does not guarantee that you don't have vulnerabilities. Using the appropriate mode of encryption guarantees that. Okay. This actually ends our discussion of block ciphers. Okay. We are still into the topic of symmetric encryption. We still actually have to discuss stream ciphers, but this ends the discussion of block ciphers. Before I go into the topic of stream ciphers, I want to discuss something that is very important. Now that we know what is an encryption algorithm such as AES, and we know how to use it using a mode of encryption, given a packet, we have to also understand which parts of the packet can we encrypt. If we remember our networks course, we know that the packet contains data. Let's say, for example, it's an HTTP request. So the data is the HTTP request itself. This is the message. This HTTP request has a group of headers. It has TCP header, has an IP header, and it has a data link layer header. Now, which part of this packet is it okay to encrypt? If you have ever seen a URL that is HTTPS, that means you are using a transport layer protocol, which is called TLS, okay, or SSL. TLS and SSL will encrypt the content and also will encrypt the transport layer header, okay, the TCP header. But it will not encrypt the IP header and the data link layer header. Which parts are okay to encrypt and which parts are not? There are actually 2 ways to do it. There is something called link encryption and there is something called end-to-end encryption. What we have just discussed, which is what TLS and SSL do, they do end-to-end encryption. End-to-end encryption means that the one that encrypts is the original sender and the one that decrypts is the final receiver. If you have routers in between them, the routers don't encrypt or decrypt anything. The routers actually just take the packet as it is and forwards them. Okay. So how can the routers actually do the forwarding? We know that the routers do the forwarding based on IP addresses. So the IP addresses in this case have to be in the clear. The routers have to read them. So if you do end-to-end encryption, you actually have to let the routers read the IP addresses. So the IP addresses in this case are vulnerable, meaning that someone who monitors your communication will be able to know who is sending and who is receiving. And this is actually what the Tor network does. It hides the identity of the sender and the receiver. Okay. Link encryption, on the other hand, has a different goal. Link encryption aims at encrypting everything, so encrypting all the headers. In order for it to do that, the routers have to be able to decrypt. So if the routers have to be able to decrypt, then the routers need to have a key. That means every router needs to exchange a key with the other router. So if you have, for example, an original sender and you have several routers in between, end-to-end encryption means that there has to be a key between the sender and the receiver. The encryption happens here and the decryption happens there. If you have link encryption, that means that there is a key between the first two devices, another key between the second two pairs of devices, a third key between the third pair of devices, and the fourth key between the fourth pair of devices. And in each stage, you encrypt and decrypt. If you do that, you can actually encrypt all the headers. Okay, this is actually the difference. In the internet, TLS and SSL achieve end-to-end encryption. IP security has different modes, but mostly it also achieves a form of end-to-end encryption, although it can have some compromise with link encryption, as we will see later in the course. Okay. Now we are actually going to start our discussion of stream ciphers, and this is going to be the last topic that we will discuss in symmetric encryption. So we have discussed block ciphers, which is a type of symmetric encryption. Now we will discuss stream ciphers. In stream ciphers, we said that the process actually is very simple. You have an XOR operation, you XOR the block of plaintext, which we said is going to be typically a small block, and you have a pseudo-random number generator that is seeded with a key. Okay? Out comes the ciphertext. Okay, so the entire discussion of stream ciphers depends on the pseudo-random number generator. So this is actually what we are going to start our discussion of stream ciphers with: how to generate random numbers. In general, random numbers actually have a lot of uses in security and in cryptography. We have already seen, for example, the output feedback mode, which relies on something called a nonce. A nonce is a random number used only once. And the output feedback mode relies on the nonce, so that when you want to encrypt something, you don't repeat the same initial value with the same key, because as we said, this will start producing patterns in the ciphertext. So a random number is something that is generated once, used only once, and thrown away. This is one of the uses of random numbers, and nonces are used also in authentication protocols, as we will see later in the course. Random numbers are also sometimes used as session keys for generating public keys, as the key stream of a one-time pad. We discussed the one-time pad in our first lecture. Okay, so random numbers have many uses. In this lecture, we will see how random numbers are generated. First, we will start with the discussion of what are actually the requirements of a sequence of random numbers. When you want to have a sequence of random numbers, what are the criteria that you have to follow? Sequences of random numbers need to have two main criteria to be evaluated for. First one is randomness. Okay, a sequence of random numbers, as you might guess, as it is logical, they have to be random. What do we mean by random? We actually mean two properties. First of them is uniform distribution. That means ones and zeros, if you are generating a random sequence of bits, each one and each zero should actually occur with the same frequency. You should not have more ones than zeros or more zeros than ones. So the frequency of occurrence of ones and zeros should be approximately equal. The second one is independence. No one subsequence in the sequence can be inferred from the other. So for example, if you have 100 bits, if you know the first 50, you should not be able to infer the next 50. Or if you know 20 bits in the middle, that should not actually help you infer another sequence of bits. So uniform distribution and independence. The second criteria is unpredictability. Each number is statistically independent of other numbers in the sequence and therefore unpredictable. Basically, if you're trying to generate these 100 bits, you generate the first bit. Okay, and then you generate the second bit, and then you generate the third bit. Each time you generate one bit, it should not be predictable based on the past bits. So it's as if you're actually flipping a coin. Every time you generate bits, you flip a coin. If it's heads, it's 1. If it's tails, it's 0. And because flipping of a coin has an equal chance to be heads or tails, then you have an equal chance to produce a 1 or a 0. It's an unpredictable sequence. You cannot predict the outcome of a coin flip. Okay, so sequences of random numbers need to exhibit randomness and need to exhibit unpredictability. The truth is, true random numbers are rarely used in commercial use. Rather than that, we actually use sequences of numbers that appear to be random, but they are actually generated using a deterministic algorithm. And this brings us to the types of number generators. You have a true random number generator. This produces actual random numbers. Okay. The only way to have a true random number generator is that you depend on something that is actually truly random. And there is nothing that is truly random unless it has some kind of physical property. For example, the exact measurement of the temperature of the weather, or the clock, or something that has true physical properties, which we call an entropy source. So true random number generators, they take as input a source of true randomness, something that has a physical property, and they just convert it to binary, and you have a random bit stream in this case. Okay. Whereas a pseudo-random number generator takes as input a seed, an initial value, and out comes a sequence that appears to be random. It appears to exhibit randomness and unpredictability, but it is generated using a deterministic algorithm. Why is this important? Because if the receiver has the same seed, it will be able to generate the same sequence. And you have different types. You have a pseudo-random number generator. It generates just a continuous stream or continuous sequence of bits. And you have a pseudo-random function that just generates a fixed number of bits. Okay. So if we are focusing on pseudo-random number generators, and this is what stream ciphers use, we have to study its requirements. So one basic requirement is an adversary who does not know the seed is not able to determine the pseudo-random string. You're basically generating a sequence of bits that appears to be random. The only way you would be able to reproduce this sequence of bits is that if you have the seed. So if the adversary doesn't know the seed, they should not be able to reproduce the string, meaning that the string has to actually be unpredictable. You cannot actually produce parts of this sequence of bits just by observing the produced bits. So the pseudo-random number generator also has to exhibit randomness. Unfortunately, there is no test for randomness. Instead, there are actually tests that see whether the pseudo-random number generator exhibits the following feature. Uniformity. Uniformity means that the generation of the next bit is equally likely to be 1 or 0. This brings us to the issue of frequency. The number of ones should actually be approximately equal to the number of zeros. The next property is scalability. If you can actually generate 100 bits, and these 100 bits appear to be random, then if you take as a sequence 50 bits, subsequence, they should also appear to be random and should also exhibit the same properties. The final property is consistency. That means the fact that the pseudo-random number generator appears to be truly random should not depend on a particular seed. Means if you change the seed, it should actually still exhibit the same properties. The seed should not actually be a factor there. Okay. This is what we want in pseudo-random number generators. We also want unpredictability. Particularly, we want forward and backward unpredictability. Forward unpredictability means that if you have a sequence of bits, you should not be able to predict the future bits that will be produced by the pseudo-random number generator. Backward unpredictability means that if you see the output of the pseudo-random number generator, you should not be able to trace back the output to determine the seed. You should not actually be able to figure out a correlation between the sequence of bits that are produced and the seed itself. Now that we know the properties and the requirements, we can see some examples of pseudo-random number generators that have been used over the past, and some of them are still used in practice. First one is a very simple one. It's called the linear congruentional generator. Basically, The numbers are generated using this equation. Okay, xn plus 1. So if you want to generate a number, this number is equal to a multiplied by the number before it plus c. All of this is mod m. So you have to choose these values. You have to choose a value of a, c, and m, and you have to choose the initial value, which is x0. x0 is what we call the seed. This is the initial value. You can choose anything you want. There are actually no requirements for these numbers, but some choices are obviously better than others. The ideal case is you want to choose a, c, m, and x0 such that you have a function that generates the full period. What do we mean a full period? Let's say if you choose m to be equal to 8, okay, a full period means that you are actually able to generate the numbers from 0 to 8. Okay, if you choose m to be equal to 16, you should have values of a, c, m, and x0 such that the numbers are generated are from 0 to 16. Okay, this is what we mean by a full period. Now, I want you to actually pause the video here and try different values of a, c, and m. Try actually having a equals 1, c equals 0, and m, for example, equals 7. Typically, we actually have m as a prime number. And then try a different value. Try, for example, a is equal to 2, c is also equal to 0, and let's actually keep the same m. Try those and see what you get. You will actually find that some numbers are definitely more secure than the others. Okay. Now, the problem with the linear congruential generator is that it is quite insecure. By observing some sequences, you will know that the sequences definitely repeat because you're using mod. There is always a limited number of sequences that can be generated. And so if an attacker observes a large enough number of generated numbers, they will be easily able to reconstruct the sequence. Okay, and so by itself, the linear congruential generator is not sufficient. If people want to use it, they usually combine it with something. They can, for example, take the output of the linear congruential generator and combine it with something that is more random. For example, the output of a clock, okay, or modify the stream using some kind of way. Okay. Obviously, the values of A, C, and M should not should be kept secret. If an attacker knows A, C, and M, they will be able to easily generate all the following numbers. So A, C, and M should be kept secret. X0, which is the seed, should also be kept secret. So if the linear congruential generator is not very secure, the next one that we will discuss is something that is used more frequently in practice, and it is called the Blum Shub generator. Basically, you have this equation, xi equal xi minus 1 squared mod n, and n is actually the product of two prime numbers. Now, the idea of the Blum Shub generator is that the numbers that are generated using this equation are not the ones that are used. You generate numbers using this equation, and then you convert them to binary. And you don't actually take this binary sequence. You take only the last number. Okay? So for example, here, you see if I equals 0, this is actually your seed. If I is equal to 1, you generate this number. If you convert it to binary, the last binary digit will be 1, because this is an odd number. X2 also generates an odd number. X3 generates an even number, and so the generated bit here is 0. This here is the sequence of bits that you take. Now, because this equation is equally likely to generate an even number or an odd number, the bit that you will take from the sequence is equally likely to be 1 or 0. And so it is unpredictable. It passes the next bit test. Okay. Obviously, the entire security of the system relies on factoring n. You see, n doesn't actually have to be kept secret. You don't really know that because the numbers themselves are not disclosed. The numbers are internal. What you disclose is just the sequence of bits, which is either the 1 or the 0. It is a little bit slow for Cipher use, but it is good for key generation because what you have to do is that you have to do this mathematical equation and you have to generate a number and you convert it to binary and take the last bit. Okay. Now we can actually discuss stream ciphers. This figure here shows you how stream cipher works, and we have discussed this before. So it relies on some form of pseudo-random byte generator, and it is seeded with the key. Okay. Now we will discuss actually the one of the popular types of stream ciphers. It's a little bit old, so it's going a little bit out of use. In fact, AES, because it is now implemented in fast hardware modules, it is overtaking stream ciphers a little bit. But RC4, it's still actually widely used in devices. For example, Wi-Fi still supports it. Okay, so how does RC4 work? Basically, you start with a key. The key can be any value between obviously it cannot be 0 bits, but its maximum can be 256 bits. Okay, what you do is you generate an array, and the array basically contains the numbers from 0 until 255. So 0, 1, 2, 3, and so on until 255. You have another array, let's call it T. You copy the key into this array, and the array also has 256 places. So if the key is shorter than 256, then you copy the key and you repeat it several times until it fills this buffer or this array. If the key is equal to 256 bits, then you just actually copy it to this T buffer. Before you encrypt anything, you take this T buffer and you do permutation to it. This is actually what you see in this code. For I equals 0 to 255, you generate this array here, which has the numbers from 0 to 255, and you copy the key to the buffer or the array Ti. This is actually the key here. Okay? And then what you do is that you permute the array S. So the array S that contains the numbers from 0 to 255 in ascending order, you permute them according to the key. Okay, so you repeat these two steps. In every step, you swap Si and Sj. So you swap two positions in the array S, and the swap depends on the value of the key. Okay, so the result of this stage is that you have a permuted array S. Okay, then if you want to encrypt, basically what you do is you take one value of the array S. So let's say now the array S contains 124, 100, 25, 56, some kind of permuted version of the numbers from 0 to 255. Every time you want to encrypt, basically you take one box of this array and you XOR it with the message that you have, and you do a swap. So every time you encrypt a block of a plain text, you swap the content of the array further another time. So the content of this S array keep changing every time you actually encrypt. Okay. This here is the summary. You start with the array S from 0 to 255. You copy into it, you generate another array T, and you copy the key into it. Then you do an initial permutation where you use T to permute S. And then when you want to encrypt, you take one box of S and you actually use it for the encryption. And then you do a swap for S as well. Okay. That ends actually our discussion of RC4 and ends our discussion of symmetric encryption. Starting next time, we will go into the second branch of cryptography, which is public key cryptography. Thank you, and we'll talk to you next time.